Hey everyone, and welcome. Today, we're going to jump right into one of the most crucial skills in data science, how to take a big pile of raw numbers and turn it into your very first meaningful insights. And we'll be using NumPy to do it, the absolute powerhouse library in Python for exploring its super fast and powerful statistical toolkit.
So picture this. You've just been handed a brand new data set. Could be sales figures, could be test scores, anything. Before you even think about building a fancy chart or training a complex model, what's the very first thing you should do? The answer to that really sets the stage for everything else.
And there it is. You have to summarize your data. Seriously, this isn't just some boring preliminary check, it is the foundation of your entire analysis. You need to get a feel for the data's basic personality. Where's its center? How spread out is it? And how do the different pieces talk to each other? This step is absolutely non-negotiable, and luckily, NumPy gives us the perfect tools for the job.
All right, let's get our hands dirty. Our first mission is to find the center of gravity for our data. Now, the two most common ways to do this are with the mean and the median. They might sound kind of similar, but trust me, they can tell two very different stories about your data.
First up is the mean, which you probably already know as the good old average. It's super straightforward. Just add up all your values and then divide by how many values you have. In NumPy, it's as easy as calling np.mean. Boom! This gives you a quick, first-glance feel for the typical value in your dataset.
And next, we have the median. Now, the key difference here is the process. To find the median, you have to sort all your data first, from the smallest number to the largest. The median is simply the number that lands smack dab in the middle of that sorted list. And of course, you don't have to do that by hand. NumPy handles all the heavy lifting with np.median.
So why do we need both? Well, this slide nails the reason. Imagine your data is a list of company salaries. You've got a bunch of regular folks earning a modest wage, but then the CEO makes millions. That one single extreme value, that outlier, is going to drag the mean salary way up. But the median? It doesn't care about that outlier. It just finds the middle person in the list, giving you a much more robust and, frankly, a more realistic picture of a typical salary.
Okay, but let's be real, data rarely comes in a single, simple list. Most of the time, we're working with tables, or in the world of NumPy, two-dimensional arrays. And to navigate these tables, we have to understand a really critical concept, the axis. Just think of it as your compass for data. Let's look at a quick example. Imagine this array here represents test scores. Each row could be a different student, and each column could be a different test. So the question is, how would we figure out the average score for each test or the average score for each student? This is where that axis parameter becomes your best friend. When we say axis equals 0, we're telling NumPy to do its calculation down the columns. It kind of squashes the rows together, calculating the mean for the first column, then the second, and so on. In our little example, this gives us the average score for each individual test. And you can probably guess what happens next. If we switch it up and say axis equals 1, or telling NumPy to work its magic across the rows, it squashes the columns for each row, giving us the average for the first student, then the second, and so on. Getting a handle on this axis concept is absolutely crucial for analyzing any kind of tabular data. Okay, so we know how to find the center of our data. That's a great start. But it's only part of the story, right? We also need to understand how spread out our data is and how different variables might be connected.
A really key measure for this is the standard deviation, which we get with np.std. This one number tells you, on average, how far each data point is from the mean. So a small standard deviation means all your data is huddled together, really tight and consistent. A big one means it's all over the place. It's a fundamental way to measure variability.
But what happens when we have two different variables? Does studying more hours actually lead to higher test scores? To answer questions like that, we can't just look at each variable by itself. We have to measure the relationship between them. And for that, we use the correlation coefficient, which we get from NumPy's np.corecoef function. This gives us a single value between -1 and +1 that kind of describes the whole relationship. A value close to +1, that's a strong positive correlation. As study hours go up, test scores tend to go up. A value near -1 is the opposite. And if it's close to 0, well, that suggests there's no real linear connection at all.
All right, let's talk about a super common, real-world problem. Data is rarely perfect. More often than not, it's got missing pieces, which can cause some major headaches for the simple functions we've been talking about.
So what happens when you have these gaps in your data, often shown as NaN, which stands for not a number? Well, if you try to calculate a simple mean on data that has even one of those NaN values, the whole thing just breaks. It's a huge pain. But luckily, NumPy has a really clever solution up its sleeve.
The solution lies in the np.average function. Now, at its core, this function calculates a weighted average, which just means some data points can be given more importance or more weight than others. If you don't give it any weights, it just acts like a normal mean. But the real magic happens when we create those weights ourselves.
So here's the trick. We can create a second weights array that's a perfect match for our data. For every valid number in our dataset, we give it a weight of 1. But for every single missing value, we assign a weight of 0. When we feed both our data and these new weights into np.averages, it effectively multiplies the missing values by 0, which makes them completely disappear from the calculation. This gives us an accurate mean using only the data we actually have. It's an incredibly powerful trick for dealing with messy, real-world data.
So there you have it. We've covered the absolute essentials: finding the center with mean and median, navigating 2D data with the axis parameter, measuring spread with standard deviation, finding relationships with correlation, and even handling messy data with a clever weighted average trick. You now have the fundamental toolkit, so the only question left is, what story is your data waiting to tell?